Okay, so my talk is about antibodies tests, and these are, I consider this a fundamentals kind of talk. There's nothing really earth-shattering in here, but it's application of definitions and then viewing them properly and understanding the implications for these serology tests. So I'll go over what these definitions are, and I'll apply how they work on different tests. I'll go over some case studies and then a brief discussion. Hopefully there will be a little bit of time. Okay, so basically we have a few different probabilities that we need to keep in mind. Of course, everybody talks about what's the prevalence of COVID-19. The other things that we need to look at are the sensitivity and specificity. So these are like the calibration measures of the test that are done before any patients are brought into the mix. And then the posteriors, which are what actually patients and doctors are most concerned about. This is the probability that you actually have the disease given you test positive, or the probability that you don't have the disease given you test negative. So the main thing to notice here is that these are different probabilities. It's a flip of the condition. So what we can show is you can use Bayes' rule to calculate, for example, for your positive predictive value, you can write it in terms of sensitivity, specificity, and prevalence, and same thing for negative predictive value. So sensitivity and specificity are tested beforehand, and then once you know the prevalence, you can incorporate those to calculate what is the positive predictive value. So among the proportion of people who test a certain way, either positive or negative, what's the proportion of those tests that are positive or that are true positives or true negatives. Okay, so those formulas also, there's a package called MKVisc that is in R. There's a function called pred values, so you can use those formulas. And then I plug those into ggplot for each test and Plotly, which sort of gave an overall picture. And our code is available on GitHub, so you can follow along and see these. And also you can play around with the plot. So I'm going to show what some of these look like in general, then we'll go over the specific test. So in general, as you may have seen in some talks today, most prevalence estimates range from either really, really low, I've heard things about 5%, 10% overall, up to about 30% in some hotspots. Then we have sensitivity. Generally, for each of the tests, you can see the FDA has authorized a set of serology tests, and the sensitivity range is about 80% and up, and the specificity is going to be really key. That's 90% and up. So we looked at all of these possibilities, and now I'm going to show you what that looks like. So this is a positive predictive value plot. Again, among those people who test positive, what proportion actually has the disease. And so you see here, this is quite variable. So looking at the range, it ranges from really low, almost 0, up to 1. So the whole probability is represented depending on your prevalence. As prevalence goes up, your predictive value improves. Same thing with as your specificity goes up, so your test is better at weeding out the negatives from positives. And then as your sensitivity goes up, as it's better at detecting the signals, the positives out there, as that goes up, your test also improves. Now, this is really interesting when you rotate it. So I'm going to show a little video of what this looks like. We did this graph in Plotly. And so what you can see is you can actually pick up the graph and rotate it. And so you can see how this varies with respect to each parameter. So again, the color indicates the sensitivity, and then the other 3 parameters are the graph. So the vertical axis, if you will, is the positive predictive value. And you can see it, it's pretty sensitive, especially to both prevalence and specificity. Now, we made another graph with respect to a negative predictive value. For the sake of time, I'll skip the video, but you can go to GitHub and you can make it, or you can email me and I'll make a little video of that. But The negative predictive value was pretty good for pretty much all of the tests in the range and all of the reasonable scenarios that we're encountering at the moment. It kind of looks like a block of cheese or a slice of cake. All right. So what does this look like for specific tests? Again, I'm going to restrict to the positive predictive values because negative predictive value was 90+% for everything. So that means that negatives are pretty well predictive. The negatives are generally true negatives. Now, what about PPV? How does this vary by sensitivity, specificity, and prevalence? Because as we all know, the case counts and therefore the prevalence is not very easy to estimate. And then also the sensitivity and specificity have some pretty wide uncertainty. And so we use the confidence intervals, the 95% confidence intervals, those. For the purpose of visualization, we're looking at prevalence in the range of 0 to 10%. We also made some graphs up to 30, but you can see that the behavior kind of levels off pretty quickly after the 10, so we restricted it here, but you can produce values easily. I can produce more values easily. So for now, I'm going to focus on what we have. So for example, one of the best performing tests at the time that this paper was written, which was in May, there was a test by Roche Pharmaceuticals. It's very, very sensitive. So you see here the specificity is 99.7% or more. It was tested on 5,000 or so people in terms of establishing the specificity. So the positive predictive value is quite good, even if you have really low prevalence. You have 60% or more percent positive predictive values. And then, of course, as you go up to 10% or more, your positives are very predictive as well. So there are fewer and fewer false positives. And so if you have a choice, what test am I going to get if I want to get tested for antibodies? As of the time of writing, the Roche test was really, it performed very well. And even as your sensitivity was less than 90%, it didn't really make as big of a difference. Now let's contrast that. Here's another test. This is by ChemBio. You see the highest we even saw was about 80%, and it went down pretty low for this particular test with the same prevalence range. You see here is, again, how does it range with your sensitivity and specificity? So here you have much lower sensitivity, so that makes sense that our positive predictive value is not as good. And the specificity also had dropped, and that's really where these positive predictive values are dropping the most, is when the specificity drops. So another thing I want to point out, what you see in this graph, it's another potentially low performing test, but you see this line here up above at the 1 range, so perfect positive predictive value. If your specificity is exactly equal to 1, the formula will automatically give you perfect positive predictive value. But this is a little bit misleading because the 95% confidence interval for specificity included 1, and because these are close to the tails, you know, close to 1 or close to 0, the estimation is actually not very stable. So I'm going to show another table of where that's concerning. What you see here in the column that says N sen/spec, this is the number that was used to validate sensitivity and specificity. So for the set of tests that was available in May at the time of writing of this paper, I know there have been at least 1 or 2 more tests since the last time I checked, and there may be even more coming out on a regular basis. But based on these 13 that were available at the time, you can see some of these numbers used for validation are very low. There's a test here, the Roche test, the sensitivity was only tested on 29 people. So you can imagine that that confidence interval for sensitivity is fairly wide. So for specificity, this is most concerning if the sample is small. So as you can see for the Euro test, it was tested on 80 people. There's another one, Mount Sinai, on 74 people. So a lot of these, the confidence interval will touch 1. So I wouldn't be super concerned, or I wouldn't put too much stock in the ones that have confidence intervals near 1. Now, we actually flipped this for visualization because most people are interested in the false positive rate. and we reported false positives at 1%, 10%. Again, these are easy to produce at any particular value. It's 1 minus the positive predictive value. So just kind of the counterpart. And what you see here is that some of these confidence intervals are quite wide. Again, you have lots of zeros here. That's counterpart to the one I was talking about. And then they range from pretty good. Here, the Roche test is well contained, very low false positives. And then you have some other ones that have 60% false positives, point estimates around a third. That's not very good. So we looked at a couple of case studies. I'm going to point out a couple of things about these pretty quickly. We had the Santa Clara test. You may have heard about this. This was a well-publicized study. It was highly scrutinized. So the prevalence estimates varied quite widely from almost 0 to up to about 5. And then even the specificity and sensitivity also range. So we used some estimates. I believe these were from Andrew Gelman and his team. And we looked, we included a pretty wide range and looked at how that could affect the positive values. So here's what the graph looks like. You can see we're looking at like a relatively low prevalence range, 0 to 5. Or these were estimates in about March and April. And what you see is, again, even if your sensitivity is 0.64, so you're looking at the red ones, it doesn't really drop that much compared to, you know, the green and the blue for a specific shape. So the shape indicates specificity, and you see like the circles are much lower than the triangles. So again, increasing your specificity just a little bit really improves your positive predictive value, but at the end of the day, the sensitivity and specificity are what they are. So we just need to be aware of this wide uncertainty range that I think often gets lost. People just look at the point estimates. So you can see there were 50 positive tests here. So if we were to think backwards, what's the positive
Naomi,
predictive
you have
value?
5 minutes.
Thank you. So how many tests are expected to be false? It ranges from very few, 2 to 14 out of the 50, to almost all of them, 26 to 46. So again, very wide range of how confident we are in estimates of the positive predictive values, as well as how many of those positives are expected to be true positives. So then we looked at New York. We thought this was an interesting test because they reported by region, and the rates varied for the state overall, and certain industrial areas that were very heavily populated, hotspots, and then some more rural areas that were not as well affected by COVID, and so they had much smaller seropositivity rates. So we looked at the test that they used, and we looked at the confidence interval and point estimates of sensitivity and specificity. And then we put that together with the seropositivity rates, using that as a proxy for the prevalence. And what you see here is, again, based on what specificity the actual test has, if you're looking at a specificity of 0.93, then there's a pretty high false positive rate. But if the specificity is at the upper limit, 99.5, then it might be a little bit less concerning in terms of the false positives, and our positive predictive values a little higher. So we need to be aware of, obviously, this range of uncertainty. And as similarly, the range of sensitivity affects it as well, denoted by the color. Okay, so how does this look in particular regions? Well, in hard-hit areas, the positive predictive value is fairly high, so 74 to 98%, or 60 to 97%. So this is like, you know, at least half or almost all of the positives are expected to be true positives, or conversely, relatively low false positives. Now, you can see this is more medium statewide and in Rockland. But if you go to some of the other areas, we had in North Country, for example, 12% to 69% positive predictive value. And then you flip that, that means you could have up to 88% of the positives were false in North Country. So overall, this meant that the false positive ranged from 2 to 88%. So the conclusions that I want to go over are basically know the definition. Sensitivity and specificity are not the same as positive and negative predictive value, but positive and negative predictive value are what doctors and patients who are looking at test results after the fact are actually interested in, because they want to know how much they should trust or potentially think about the uncertainty of these test results. So negative predictive value was pretty high, and positive predictive value was kind of all over the map, and there's a potential for high rates of false positives. So we use these two tools to visualize that. Couple things to highlight really quickly. Again, overall test accuracy is high because when the prevalence is low, we expect most tests should be negative. So the fact that there are lots of true negatives actually drowns out the false positives that we get. So I just want to point that out. And then what are the implications of false negatives? Well, it probably means that somebody thinks, okay, I never had COVID, but I actually did. They'll probably be extra cautious. But the bad implication here is that convalescent plasma could have potentially been used, and it will be left on the table and not used. On the other hand, having lots of false positives is potentially really dangerous, because then somebody might think, oh, I was exposed, and they might relax social distancing, mask wearing, etc. So you need to be careful of having false positives, because people's behavior may change. Also, just pointing out there's a difference between prevalence and seroprevalence, but they tend to potentially correlate. There was an interesting talk earlier that talked about when they did and when they did not. Okay, so just if you have other questions about this, please feel free to email me, and we have our paper is on medRxiv, and you can browse through our code and everything else. So I'm happy to answer any questions over email or now or later. Thank you.
There was one question I wonder if you could answer this quickly. Is
Sure.
Where are the sensitivity and specificity coming from, and is the company reporting it?
Yeah, so that website that I linked was from the FDA. So the FDA reports those amounts. Now, I don't know if they are pulling it from the company, if they back check what the company reported. I can't really speak to that, but I can say that website is an FDA website.